Okay, we're going to be talking about absolutely convergent and conditionally convergent. So when you have a series, if it converges normally, then to figure out if it's absolutely convergent, you also want to figure out if the absolute value of it converges. For example, if you have a series like this, you also want to know if the absolute value of it converges. And this is normally talking about series that are alternating or that have negatives. So you're trying to figure out if these two both converge. If this one converges and the absolute value converges, it's absolutely convergent. But if only the original converges, but not the absolute value, then it would be conditionally. And then if neither converge, then it's obviously divergent. So let's look at some examples. Let's talk about this one here. Alright, first of all, this one doesn't look like it's alternating, but just to remind you, it is alternating because we have sine of n, and if I plug in values here, I know that, especially if I think about pi over 2 and pi and those kinds of numbers, this is going to go back and forth from positive to negative. So when I think about the absolute value of it, the absolute value of it is 1 over n squared. Okay, so the absolute value is to get rid of the sine of n. I know that this converges by the p-series. So the real question is, does the original converge? If the original converges and the absolute value converges, then it's absolutely convergent. So we need to figure out, does this converge or not? Easiest way to figure that out is to take sine of n over n squared and compare it to 1 over n squared using the direct comparison test. And if you do that, what you will find is that this will be less than this. This converges by p-series, which we already know, and because this is a less value, I know that it will also converge. So the original converges by direct comparison test. The absolute value converges by the p-series, so this series is absolutely convergent. Okay, let's look at this example. Alright, so I can tell this is alternating for sure. And so what I would do first is to say that the alternating series converges by AST. And think about your two conditions there. Each term does continue to get less. And so both conditions of the AST, the limit, also equals 0, but both conditions work, so it converges by AST. So then I want to figure out, well, what about 1 over n? Does 1 over n converge? Because 1 over n is the absolute value of this, because it just takes off that part, make it not negative. This actually diverges by the p-series. So because the series itself converges, but the absolute value does not, this one is conditionally convergent. Now, when you're trying to tell me if something is conditional or absolute, I'm going to want to know, okay, what the original one converges by and what the absolute value converges or diverges by. So you should have reasons for both of those. You might not have to have all of the work, but you do need to be able to tell what's going on. Alright, so separately I'm going to look at, okay, does the alternating series converge? And then I'm going to figure out, does the absolute value converge? Remember, absolute value just takes off that negative 1 to the n. This does converge by AST. The limit does equal 0, and each term continues to get less. On AST, you can kind of just, like, in your mind think about it. You don't have to write it down every time, unless I say, show me it converges by AST. This one is geometric. If you want to rewrite it as 1/2 to the n, you can. I realize that r is less than 1, so this one converges by the geometric series, which means this is absolutely convergent. Okay, so here's another problem. Again, we're going to look at the alternating series, and we're going to look at the absolute value of it, which just gets rid of that -1 to the n. This converges by AST. Each term is getting less. The limit is also equal to 0. This diverges by the p-series because p is 1/2. Remember, if the p is less than 1, it diverges. And so what that means is this is conditionally convergent. Okay, here we have another one. First of all, when you talk about this series, if you don't even think about the -1 to the n, just think about the n factorial, what's going on is that each term is actually getting greater because we're talking about n factorials, and so we're talking about greater and greater numbers. And so, like, it's getting greater, but then the negative is, like, coming down here, but still the positives are getting greater and the negatives are getting greater, so they're going away from each other. This diverges. And basically we use the nth term test to figure it out because we looked at this right here. You could also say it diverges by AST because each term is getting greater. And because that diverges, we don't even have to figure out about the absolute value. The absolute value also diverges. But the series itself diverges. So it might not be conditionally or absolutely, it's just diverges. And then one other one to look at is this one here. And then I want to look at 1 over ln of n plus 1. I will tell you this one again converges by AST. Most of the time, if you can do the alternating part, that will give you the first part of it. The next part's the part you sort of have to figure out. This is easiest to, well, there's lots, you can't really do nth term because you would get a 0, but I could compare it to 1 over n. And I think using the direct comparison test, it would be greater. And so if this is 1 over n and this is greater, and this diverges by the p-series, because this is greater, this will also diverge. So the -1, the alternating converges, but the one without the absolute value, or without the negatives, the absolute value diverges. That means that this is conditionally convergent.